The last topic to cover in chapter 10 deals with elastic collisions. Let us consider the case of two objects M1 and M2 colliding. Let us assume that M1 is moving to the right with initial velocity v1I, and let us also assume that M2 is stationary, so the initial velocity is 0. Now, elastic collision we can model by imagining that there is a spring in between the two objects that is, of course, at its unstretched length to start with. So this is the scenario here is before collision, and during collision the spring is compressed. So this is during collision. When the spring is compressed, there is an equal spring force exerted on both objects M1 and M2, but of course in opposite directions. So the forces are F1 and F2 respectively, and the spring force causes the two objects to repel each other, so they bounce off each other, and the spring returns to its unstretched length, and M1 and M2 have now assumed their final velocities v1f and v2f respectively. So this scenario here is after collision. Now if we choose our system, if we define our system to include M1, M2 and the spring, then you see that what we have, there is no friction type forces involved. There's no external force being applied to the system that I've enveloped in the green border. That means that the change in the mechanical energy of the system, E mechanical, must equal 0. So if the change in the mechanical energy of the system is 0, that means the energy mechanical before must equal energy mechanical after. And furthermore, since there is no external force involved, we also know that change in the momentum, total momentum of the system must also be 0. So since there is no friction type forces involved, total mechanical energy is conserved, and since there is no external force being applied to the system, then total momentum is also conserved as well. So let us go ahead and write the energies that are factored into our system. We have kinetic energy for object 1. We have kinetic energy of object 2, which in this case is 0 because it's not its initial velocity is 0. And of course we have spring potential energy initial, which is also 0 because our spring is neither compressed nor stretched. Therefore, total mechanical energy initial is E mechanical initial is simply K1I plus K2I plus USI. And after collision, once again, this is our system here. So after collision, we have K2 final plus, K1 final rather, plus K2 final plus US final. But again, US final is 0 because our the spring returns to its unstretched length. So this is the unstretched length of the spring. So the spring energy is 0, which means that the kinetic energy of the system, the sum of the kinetic energy initial is equal to kinetic energy after. Therefore, in an elastic collision, if we have an elastic collision, not only momentum is conserved, but also kinetic energy is conserved. And this is of course the condition that you have to satisfy here is that there exists no friction like forces. So change in the kinetic energy is zero in an elastic collision. That was not the case for inelastic collision, if you recall. In an inelastic collision, the two objects that collide stuck to each other, and the kinetic energy was not conserved. So writing out the expressions for both momentum, conservation of momentum and conservation of kinetic energy. Well, from change in momentum being zero, we can write we can write this equation out. This is simply momentum initial, and this is momentum final for the system. And since from change in kinetic energy being zero, we can write this expression out. Once again, this here is the sum of the two kinetic energies, so that's kinetic energy initial for the system, and that's kinetic energy final for the system. So this is a pair of simultaneous equations where velocity, where we know where velocity 1 final and velocity 2 final are the two unknowns. So we can now go ahead and solve this pair of simultaneous equations, and we end up with these relationships here, which relate final velocity of object 1 in terms of initial velocity that object 1 has, and the final velocity of object 2 in terms of the initial velocity of object 1. If I go back to the drawing that we had, if you remember, we know our masses, and we knew the initial velocity of object 1, and we said that object 2 is at rest. So you can go ahead and use these relationships to figure out the final velocities of either object 1 or object 2, but knowing the initial velocity of object 1, but provided object 2 is at rest to start with. So v2i must equal 0 for these two equations to be valid. Please make a note of these equations in your equation sheet. They'll be handy come exam time. Now, as I said, here's the picture again. We know mass 1, we know mass 2, and we know initial velocity 1, and this is 0. The velocity of the object 2 is 0 to start with. After collision, these are the unknowns, v1f and v2f, and you use these relationships here to figure out what those unknowns are. Now, what if velocity 2 were not 0? If velocity 2 were not 0, then you would have to use the Galilean transformation, which says 1 initial is equal to v1i minus v2i. This is the Galilean transformation for defining a new relative velocity for object 1, v1i prime. That's a relative velocity of object 1 in which v2 initial prime now becomes 0. So this is like making mass 2 our reference frame, putting our reference frame on mass 2. So here's our observer standing on mass 2, moving with this velocity v2i, and using the Galilean transformation, we now define a relative velocity for mass 1 with respect to the moving reference frame which is situated on mass 2. Of course, if our reference frame is situated on mass 2, that means that v2i prime is 0. So now we can go ahead and use the relationships we had, except remember that now you have instead of v1i, we have v1i prime here, and you will end up with v1f prime and v2f prime in this case, after figuring out the final velocity v1f prime and v2f prime, after figuring out the relative velocity, the relative final velocities, then you have to use the reverse Galilean transfer function to transfer these velocities into our stationary reference frame. So v1f and v2f. So you have to use the reverse Galilean transfer functions to transfer them back. In fact, v2f would equal v1f prime plus v2 initial, and v2f would equal v2f prime plus v2 initial. So these would be the inverse transformation functions. So just a quick recap. In an elastic collision, both momentum and kinetic energy are conserved. It's the most important thing to remember, that both momentum and kinetic energy are conserved in an elastic collision, and that if the second object is stationary and the first object has some initial velocity, then you can use the relationships here to calculate the final velocities of object 1 and object 2. And if the second object is not stationary, then use the Galilean transfer function to essentially deal with the moving reference frame in which our second object becomes stationary in that reference frame, and then having figured out the final relative velocities for objects 1 and 2, then use the inverse transformation functions to come up with values for final velocities of object 1 and 2 in our original stationary reference frame.